Welcome to our presentation on electrical machines. This course designed to help you to take note and summarize and discuss the main points of the video. This presentation is organized as follows: Introduction to electrical machines, classification of electrical machines, static machines, power transformer construction, rotating machines, synchronous machines, induction motor, motor asynchron, nameplate.
Let's begin by talking about electrical machines. An electrical machine is a device that takes advantage of electromagnetism to transform electricity into movement, or it can do the opposite, turning movement into electricity. These machines are incredibly important in various areas like producing power, running electric cars, operating industrial machinery, and much more. Now, let's delve into the classification of electrical machines. Electrical machines can be broadly divided into two main categories: rotating machines and static machines. Rotating machines are those with moving parts, like rotors, and they fall into two subcategories. DC machines. These include DC generators, which produce direct current electricity, and DC motors, which use it for mechanical movement. AC machines. AC machines are further divided into two types: single-phase or three-phase synchronous machines. These machines can either work as motors or generators, depending on their application. Single-phase or three-phase induction machines. These are commonly used in various industrial applications for their versatility and efficiency. On the other hand, static machines don't have moving parts. An example of this is the transformer, which is used for various tasks like changing voltage levels, isolating circuits, and more. These classifications help us understand the different roles and functions of electrical machines in various applications. In this lesson, we will delve into the world of electrical machines, where we'll cover various essential aspects. We start with the first one, the presentation of electrical machines. In this section we will understanding the significance and applications of these devices. For the second section is about the construction of electrical machines. In this section we will exploring how these machines are built and assembled. For the third section we will present the schematic of electrical machines. In this section we will gaining insights into the circuitry and connections within these devices. The other section is about the nameplate of electrical machines. In this section we will learning how to interpret the information provided on the nameplate, including ratings and specifications. Before the end of this lesson we will give you the working principles of electrical machines. In this section we will discovering how these machines convert energy from one form to another. At the end of this lesson, the useful parameters of electrical machines. In this section we will identifying key parameters for performance assessment and control. This knowledge will serve as a foundation for understanding the operation and applications of electrical machines in various fields of electrical engineering. Let's move on to discussing static machines. These are electrical devices designed without moving parts, dedicated primarily to the transformation and manipulation of electrical energy. One of the most widely known static machines in the field of electrical engineering is the transformer. This essential component plays a fundamental role in managing electricity, facilitating voltage changes, and enabling efficient transmission of power across different circuits. Now, let's explore the fascinating world of transformers. A transformer is a passive electrical device designed to transfer electrical energy from one electrical circuit to another, all thanks to the principle of electromagnetic induction. Transformers are incredibly versatile and are used for several important functions. The first one is the step-up transformer. This type of transformer is used to increase low AC voltages at high current. It plays a crucial role in power distribution, allowing us to elevate voltage for efficient long-distance transmission. The second one is the step-down transformer. Conversely, a step-down transformer decreases high AC voltages at low current. It's commonly used in applications like providing lower voltages for household appliances from the main power supply. The third is signal processing. Transformers find application in coupling the stages of signal processing circuits, enabling impedance matching and signal conditioning. The fourth function is isolation. In some cases, transformers are used for isolation purposes. In this scenario, the voltage at the input, primary coil, equals the voltage at the output, secondary coil, and the coils are not electrically bonded to each other, providing electrical isolation. Transformers, in various forms, are essential components of modern electrical systems, making them a cornerstone of electrical engineering. Now, let's talk about a critical parameter in transformers, the transformation ratio. Often denoted as A, the transformation ratio is key to understanding how transformers work. It represents the ratio between the number of turns in the primary coil, N1, and the number of turns in the secondary coil, N2. Additionally, the transformation ratio can also be expressed in terms of voltage, where transformation ratio equals N1 divided in N2 equals V1 divided into V2. Here, V1 and V2 are the voltages on the primary and secondary sides, respectively. This ratio is fundamental in determining how the transformer steps up or steps down the voltage between its primary and secondary coils. Transformers are pivotal in electrical power distribution. They enable efficient transmission of electricity over long distances, provide safe and usable voltages for various applications, and serve as essential components in electrical circuits. Understanding the transformation ratio is essential for grasping the workings of these remarkable devices. Now, let's get into the construction of a transformer. Transformers are indispensable electrical devices designed for the efficient transfer of electrical energy from one circuit to another. Their construction is carefully engineered to minimize energy losses and optimize overall performance. Here's a closer look at the key elements that make up a transformer's construction. The first element is the core, and that the transformer cores are composed of thin laminated sheets of iron or steel, stacked together. These laminations serve a crucial role by reducing eddy current losses. They help direct the magnetic field along a specific path, ultimately enhancing the transformer's efficiency. The second element is the windings, and that the transformer windings are the coils of wire responsible for transferring electrical energy between the primary and secondary sides of the transformer. Windings are typically arranged in a concentric fashion to minimize flux leakage and ensure efficient energy transfer. The number of turns in the primary and secondary windings, as well as their wire sizes, determine the transformation ratio and various other characteristics of the transformer. The meticulous construction of transformers is essential to their role in power distribution and various electrical applications. Transformers experience different types of losses, which are vital to consider for efficient operation. Core losses. These include hysteresis and eddy current losses. Hysteresis losses occur as the magnetic field in the core reverses, leading to energy loss due to hysteresis. This effect is caused by the movement of magnetic domains within the core material, often made of steel. Eddy current losses. Eddy currents are induced in the conductive core material, usually iron or steel, when the magnetic field changes. These currents flow through the core's resistance, resulting in energy dissipation in the form of heat. The use of laminations in the core effectively minimizes these losses. Winding losses. These primarily result from Joule heating, caused by the resistance of the wire used in the transformer windings. As the frequency of the alternating current increases, factors like skin effect and proximity effect come into play, leading to increased winding resistance and associated losses. Let's take a closer look at the transformer nameplate. This unassuming plate is a treasure trove of information about the transformer, and it's crucial for electricians, engineers, and maintenance personnel who work with these devices. Here's what you can typically find on a transformer nameplate. Transformer rating. The kVAR rating. It represents the transformer's capacity to handle electrical power. Voltage ratings. Primary voltage. Specifies the input voltage. Secondary voltage. Indicates the output voltage. Frequency. The rated frequency, typically 50 Hz or 60 Hz for standard power systems. Impedance. The percentage impedance, %Z, which measures the transformer's ability to withstand short circuit conditions. Temperature rise. Specifies the temperature rise above ambient under full load conditions, ensuring safe operation. Connection. Information about the winding connection, such as delta or Y for both primary and secondary sides. Cooling class. Indicates the method used to dissipate heat, like Onan or ONIF. Insulation class. Specifies the insulation system, indicating thermal capabilities and dielectric strength. Manufacturer information. Details about the manufacturer, essential for warranty, maintenance, and service. Serial number. A unique identifier for tracking and identification. Efficiency. Some nameplates may provide efficiency information at different load levels. Total weight. Weight information for transportation and installation considerations. The transformer nameplate is an indispensable reference, ensuring that the transformer operates within its specified limits, preventing overloading and damage. This information is also vital for planning electrical distribution systems and making connections within power networks. Let's delve into the fascinating world of power transformers, complex and essential electrical devices designed to transfer energy between circuits. Their construction comprises several key components and features, each serving a critical role for their proper operation. Here's a breakdown of the construction of a power transformer. 1. The tank. This serves as the outer enclosure, providing protection and insulation. 2. The lid. It covers and seals the top of the tank, securing the internal components. 3. The conservator tank, often located above the main tank, it contains insulating oil and manages oil expansion and contraction. 4. The oil level indicator provides a visual indication of the oil level in the conservator tank. 5. The Buchholz relay, a protective device that detects gas bubbles due to internal faults. 6. The piping connects various components and facilitates oil circulation. 7. The tap changer allows for adjusting the transformer's turns ratio to regulate output voltage. 8. The drive motor for tap changer, responsible for changing the transformer's taps. 9. The drive shaft for tap changer connects the drive motor to the tap changer mechanism. 10. The high voltage HV bushing provides high voltage connections. 11. The high voltage bushing current transformers measure current with high voltage bushings. 0.13 Low voltage LV bushing provides low voltage connections. 14. Low voltage current transformers measure current with low voltage bushings. 15. Bushing voltage transformer for metering measures voltage for metering and protection. 16. Core made of laminated steel sheets, serving as the magnetic path. 0.17 Yoke of the core connects to the core, completing the magnetic circuit. 18. Limbs connect the yokes and hold them up. Structural components supporting the yokes and core. 0.19 Coils windings of insulated conductors, creating primary and secondary windings. 20. Internal wiring between coils and tap changer connects coils, the tap changer, and other internal components. The construction of power transformers is a marvel of engineering, combining these elements to facilitate efficient energy transfer between circuits. Now, let's shift our focus to the fascinating world of rotating machines. These are a fundamental category of electrical devices, characterized by their moving parts. They serve crucial functions and are further categorized into DC machines. This category includes DC generators and DC motors. AC machines. This category comprises AC generators, alternators, and AC motors, further classified as single-phase or three-phase synchronous machines. These versatile machines can operate as both motors and generators. Single-phase or three-phase induction machines. Commonly found in various industrial applications, they play a pivotal role in electrical systems. Let's dive into the realm of DC machines. These electromechanical devices are indispensable for converting electrical energy from a direct current, DC, power source into mechanical energy, ultimately resulting in rotary motion. The magic happens through the interaction between magnetic fields and conductors, facilitating this seamless energy conversion. DC machines come in various types, each tailored to specific characteristics and applications. They are versatile and find use in a wide range of industries and electrical systems. DC machines offer a versatile array of types, each precisely designed to provide to specific applications. Let's explore these types. 1. Separately excited DC machine. In this type, the field winding receives an independent source of excitation, granting precise control over the field strength. It's all about fine-tuning. 2. Shunt DC machine. Shunt DC machines establish a parallel connection, shunt, between the armature winding and the field winding. They are renowned for their steady speed characteristics. 3. Series DC machine. Series DC machines connect the armature and field windings in series. This configuration provides high starting torque, making them ideal for applications that demand such capabilities. 4. Cumulatively compound DC machine. This type combines the best of both worlds by incorporating two field windings in parallel with opposite polarities. It strikes a balance between speed regulation and torque, making it a versatile choice. Each type has its unique set of advantages and applications, ensuring that DC machines find their place in a wide range of industries and scenarios. DC machines are the workhorses of many industries, thanks to their versatile and precise performance characteristics. Let's explore some of the common applications where DC machines play a pivotal role. 1. Cranes. DC motors are the driving force behind crane systems, ensuring precise control when lifting and lowering heavy loads. 2. Conveyors. In factories, warehouses, and distribution centers, DC motors power conveyor belts, facilitating the seamless movement of materials. 3. Pumps. DC pumps are the go-to choice for fluid transfer, water circulation, and applications demanding meticulous control. 4. Fans. DC motors ensure efficient air circulation in various types of fans, including ceiling fans and exhaust fans. 5. Machine tools. Essential components in machine tools such as lathes, milling machines, and grinders, DC motors enable precise and controlled machining processes. 6. Air compressors. DC motors drive air compressors used in a wide array of industrial applications and pneumatic systems. 7. Toys. Battery-operated toys come to life with the help of small DC motors, providing movement and animation. 8. Motor starters in cars. In the automotive world, DC starter motors are responsible for initiating the internal combustion engine. These applications showcase the exceptional controllability and reliability of DC machines, making them an indispensable part of various industries, where they provide the mechanical energy needed for a multitude of tasks. Let's take a closer look at the intricate construction of a DC machine. These electromechanical wonders consist of several key components working harmoniously to transform electrical energy into mechanical energy. The primary parts of a DC machine include 1. Yoke frame. This sturdy component, often crafted from cast iron or steel, provides mechanical support, forming the outer frame of the machine. 2. Pole and pole core. The pole serves as an electromagnet, with the field winding wound around it. When the field winding is energized, it generates a magnetic flux within the pole core. 3. Pole shoe. An extension of the pole shoe increases the surface area, enabling the efficient spreading of magnetic flux within the air gap. This facilitates more flux to reach the armature. 4. Field windings. Typically made of copper, these field coils are wound around the pole core. When an electric current flows through them, they create an electromagnetic field in the poles, generating the essential magnetic flux. These components work in harmony to create the magnetic field needed for the DC machine's operation. When the integral armature rotates within this magnetic field, it induces electromotive force, EMF, and facilitates the conversion of electrical energy into mechanical energy. The direction of rotation and the torque produced are determined by the current's direction and magnitude flowing through the armature windings. Additionally, DC machines may include other crucial elements, such as commutators, brushes, and armature windings. The commutator converts alternating current within the armature into direct current, ensuring a unidirectional flow of current through the windings and producing the desired mechanical output. The brushes maintain electrical contact with the commutator as the armature rotates, ensuring smooth and continuous operation. Now, let's explore the intriguing world of synchronous machines. These electrical machines are known for a remarkable characteristic. Their rotating speed is directly proportional to the frequency of the alternating current supply, and it remains independent of the load. This unique property sets them apart in the realm of electrical machinery. Within the family of synchronous machines, we encounter the synchronous generator. This particular type of synchronous machine excels in the conversion of mechanical energy into electrical energy, delivering alternating current AC at a specific voltage and frequency. You may also hear them referred to as alternators, given their prominent role in generating electrical power. They play a crucial role in various applications where a stable and consistent AC power supply is required. Now, let's delve into the types of synchronous generators. These generators come in two distinct designs, each catering to specific requirements. 1. Salient pole type. In this design, the rotor features protruding pole pieces, resulting in salient poles. These generators are the choice when applications demand variable speed and high torque. Their distinctive design makes them suitable for such scenarios. 2. Smooth cylindrical type. In contrast, smooth cylindrical rotor generators have a rotor with a smooth pole-less surface. This design is preferred when applications require high speed and a constant synchronous speed. They are instrumental in situations where stability and consistency are paramount. These two types of generators offer versatile solutions to meet diverse electrical power generation needs. Now, let's uncover the main components that make up a synchronous generator. These components are pivotal for the generator's operation, ensuring the conversion of mechanical energy into electrical power. Let's take a closer look. 1. Stator. The stator serves as the stationary part of the generator. It carries the three separate, three-phase armature windings, each physically and electrically displaced from the others by 120 degrees. This arrangement results in an AC voltage output. 2. Rotor. The rotor plays a critical role in the generation of electricity. it has two primary configurations. First, it may contain permanent magnets that provide the necessary magnetic field. In this case, there's no need for an external power source to create the field. Alternatively, the rotor can be equipped with wound field coils connected to an external DC power source via slip rings and carbon brushes. These wound field coils create the magnetic field when a direct current is applied to them. Synchronous generators are indispensable in various applications, particularly in power generation and distribution systems. They provide a stable and synchronous source of electricity, ensuring grid stability. The choice between the salient pole and smooth cylindrical types depends on the specific requirements of the application, allowing for versatility and addressing diverse electrical power generation needs. Let's turn our attention to the fascinating world of synchronous motors. These are AC motors with a unique characteristic: they are meticulously designed to operate in such a way that, at a steady state, the rotation of their shaft is synchronized with the frequency of the supplied alternating current, AC. In simpler terms, the motor's rotation period matches precisely with an integral number of AC cycles. This synchronization is at the heart of their operation and sets them apart in the world of electric motors. Now, let's explore the inner workings of the synchronous motor. The fundamental operation of a synchronous motor hinges on the rotor's remarkable ability to synchronize with the rotating magnetic field generated by the stator. Here's how it works. Rotor synchronization. The rotor is meticulously designed to rotate at a speed that closely approaches the speed of the rotating magnetic field created by the stator. This synchronization is a crucial aspect of its operation. Key components. Rotor winding. The rotor winding is excited by a direct current DC source, creating a magnetic field within the rotor. Stator winding. In contrast, the stator winding is excited by an alternating current AC source, generating a rotating magnetic field within the stator. The magic happens when these two magnetic fields interact. The rotating magnetic field of the stator and the magnetic field generated by the rotor's DC source work together, compelling the rotor to rotate in perfect synchronization with the stator field. This precise coordination is what sets the synchronous motor apart in the world of electric motors, making it a valuable asset in various applications where synchrony is of paramount importance. Now, let's explore the diverse applications of synchronous motors. These motors prove their worth in various areas, offering distinct advantages. Here are some key applications. 1. Power factor correction. Synchronous motors are a powerhouse in improving the power factor of a system. This enhancement results in greater system efficiency, making it a valuable asset. 2. Voltage regulation. They play a crucial role in voltage regulation, helping to stabilize and maintain consistent voltage levels within power systems, ensuring smooth and reliable operation. 3. Low speed, high power loads. Synchronous motors shine in applications that demand low speeds and high power outputs, making them the go-to choice for specific industrial requirements. 4. Air and gas compressors. These motors are commonly found in air and gas compressors, where they ensure precise control and energy efficiency, an essential combination for these applications. 5. Crushers, mills, and grinders. In machinery like crushers, mills, and grinders, synchronous operation is essential. Synchronous motors deliver the synchrony needed for efficient and effective performance. 6. Exhausters, fans, and blowers. Synchronous motors are also used in exhausters, fans, and blowers to maintain precise control over airflow and pressure, contributing to reliable ventilation and gas flow management. In essence, synchronous motors are the preferred choice in applications where precise control, power factor correction, and synchronization with the AC power supply frequency are vital for efficient and effective operation. Their versatility and reliability make them indispensable in these various applications. Let's dive into the heart of synchronous machines and explore their construction. Whether it's a synchronous generator, alternator, or a synchronous motor, the way these machines are put together is essential to their functionality and operation. Here's a breakdown of the key components and elements involved. 1. Stator. The stator is the stationary part of the machine. In a synchronous generator, it's responsible for carrying the 3 separate armature windings, each physically and electrically displaced from the others by 120 degrees. These windings play a vital role in producing the AC voltage output. 2. Rotor. On the other hand, the rotor is the rotating part of the machine. It carries the magnetic field, which can be created either by permanent magnets or wound field coils. If it uses wound field coils, they are connected to an external DC power source via slip rings and carbon brushes. The rotor's magnetic field is the key to inducing a voltage in the stator windings as it rotates. 3. Field windings. Field windings are usually present in synchronous generators. These are coils wound around the poles of the rotor. Their job is to create a magnetic field when an external DC current is applied. The strength and control of this magnetic field are pivotal in regulating the generator's output voltage and frequency. 4. Salient pole type. Some synchronous machines, especially generators, have salient poles. These poles are physically distinct and project outward from the rotor core. This unique pole shape enhances the magnetic field's interaction and control, allowing for precise voltage and frequency regulation. 5. Smooth cylindrical type. In contrast, some synchronous machines have smooth cylindrical rotors with a uniform diameter. This design is more commonly found in synchronous motors. While it may offer less control over voltage and frequency, it provides smoother and more stable operation. These components collaborate to ensure that a synchronous machine maintains synchronization with the frequency of the supplied AC current, which is absolutely essential for their efficiency and functionality. This synchronization is at the core of their various applications, such as power factor correction, voltage regulation, and powering low-speed, high-power loads. Next, we move on to asynchronous machines, also popularly known as induction motors. These are AC electric motors that operate on the principle of electromagnetic induction. What sets them apart is the fascinating way they generate motion. In these motors, the rotor's electric current, which is essential for producing torque and driving the motor, is induced by the magnetic field generated by the stator winding. And here's a remarkable feature: these motors don't require any electrical connections to the rotor itself. This unique characteristic makes them incredibly robust and versatile, rendering them suitable for a wide array of applications. Let's explore the types of induction machines, which are categorized based on the design of their rotor. There are primarily 2 types. 1. Wound rotor. In wound rotor induction motors, the rotor windings are made of insulated wire. What's interesting about them is that they can be connected to external resistors. This unique feature allows for a degree of control and adjustment of the motor's performance, making them suitable for specific applications that require fine-tuning. 2. Squirrel cage rotor. On the other hand, we have squirrel cage induction motors. These motors have a rotor design that consists of laminated iron cores and conductive bars arranged like a squirrel cage. This design is more common and offers a level of simplicity and robustness that is highly valued in a wide range of applications. These distinctions in rotor design give each type of induction machine its unique characteristics and advantages. Moving on to a critical parameter in the world of induction motors: slip. The slip is a fundamental concept that quantifies the difference between the synchronous speed and the actual operating speed of the motor. It's a value often expressed as a percentage or a ratio, and here's how you calculate it. S equals ns minus nr divided in ns, where S is the slip, and it's usually represented as a decimal fraction when using this formula. Then S stands for the synchronous speed of the motor, which is the theoretical speed at which the rotating magnetic field produced by the stator would turn if there were no slip. It's directly related to the supply frequency and the number of poles in the motor. Then R is the actual rotor speed, which is typically less than the synchronous speed due to the slip. It's the effective speed at which the rotor turns under the influence of the rotating magnetic field. The slip is an absolutely essential parameter for understanding and analyzing the performance of induction motors. It has a significant impact on the motor's torque, efficiency, and power factor. But its real significance comes into play when we examine how the motor behaves under load conditions. It tells us how far the motor speed deviates from the ideal synchronous speed, and this, in turn, influences the motor's ability to effectively perform mechanical work. Let's dive into the construction of asynchronous motors, also known as induction motors. These motors consist of two main parts. Stator. The stator is the stationary component of the motor and is typically made from ferromagnetic material. This material allows the magnetic field to pass through it easily. The stator serves as a support for other motor components. Inside the stator, there is a copper or aluminum coil. This coil is connected to the power supply network or a variable frequency drive, and it's responsible for creating the stator's magnetic field. Rotor. The rotor is the rotating component of the motor, and it's usually constructed as a cylinder made from ferromagnetic material. Like the stator, the rotor allows the magnetic field to pass through it easily. The rotor is connected to the stator via bearings. Within the rotor, there's a winding made up of copper or aluminum conductors. These conductors are in a short circuit configuration, meaning they form closed loops. When the motor is in operation, these conductors are subjected to induced currents generated by the magnetic field produced by the stator currents. It's important to highlight that asynchronous motors differ from synchronous machines. Unlike synchronous motors, asynchronous motors do not rely on permanent magnets or direct current (DC) coils in the rotor for their operation. Instead, they induce currents in the rotor conductors due to the rotating magnetic field created by the stator, and this interaction produces the motor's motion. Let's take a closer look at the motor asynchron nameplate, which provides critical information about the motor's specifications and ratings. This information is essential for understanding how the motor operates and its compatibility with various applications. On the nameplate, you'll find several key details. Supply frequency. The motor is designed to operate with a main supply frequency of 50 Hz. Rated output power. The motor has a rated output power of 15 kilowatts, indicating its ability to produce mechanical power under rated conditions. Stator winding configuration. The stator windings can be connected in either a star or delta formation. When connected in a star configuration, the motor current is 27.5 A per phase. However, when the windings are connected in a delta formation, the motor current increases to 48.7 A per phase. Motor protection rating. This rating indicates the degree of protection provided by the motor's enclosure against the penetration of liquids and foreign bodies. The specific protection rating should be mentioned on the nameplate, such as IP54 or IP65. Power factor, COSO. The power factor represents the share of the active current, real power, as a percentage of the total motor current at rated operation. A higher power factor indicates more efficient power utilization. Rated speed. The rated speed of the motor is the rotational speed at which the motor is designed to operate under rated conditions. This includes rated voltage, rated frequency, and rated load. Cooling method. Electric motors are designed for various types of cooling to dissipate heat generated during operation. The cooling method is typically indicated in accordance with international standards, such as IEC Publication 34-6. These details on the motor nameplate provide a comprehensive understanding of the motor's capabilities and characteristics, helping engineers and technicians make informed decisions when selecting and operating these motors.